Welcome everyone. Today we have a colloquium given by Professor Carl Rodriguez. Carl is now assistant professor at Carnegie Mellon in University, or wait, Carl told me earlier today you say Carnegie Mellon University, okay. And he has recently joined and now have many students and lots of stuff happening, so it's going to be really exciting to hear his talk today. Carl did his PhD at the Northwestern University in Chicago, working on the dynamics with black holes and a cluster dynamics also, I think. And then he had a Pappalardo postdoctoral fellowship at the MIT, and after that an ICT fellowship at Harvard for a year, and then he got this faculty job at Carnegie Mellon. So Carl is an expert on dynamics and black hole physics, and I think you will, if you think it's very exciting, you should sign up to talk to Carl. He probably still has some slots left. You can edit your schedule if you want, Carl. I send the link.
Okay.
Okay.
Well,
so
awesome.
Take it away.
Okay. Well, thank you very much, Ilva. I'm really excited to be giving this talk today. I'm a little sad that I didn't get to give it in person because I've never actually visited Carnegie. That's also something else I've noticed weird. I've only been a professor at CMU for a month, but apparently everyone in Pittsburgh insists that it's pronounced Carnegie, but no one outside of Pittsburgh has ever heard of this. I have no strong preference myself, but it's a weird little regionalism that I found somewhat cute. Anyway, I'm going to go ahead and get started, and I always like to start my talks with this slide right here, which is basically the state of knowledge about stellar mass black holes circa 2015. So going from the first detection in around 1968 of the first black hole, all the way up until almost 50 years later in 2015, this was every stellar mass black hole we knew in the local universe. They ranged in masses roughly from 5 to 15 solar masses. There were a couple of claimed extragalactic candidates that were 20 or 25 solar masses. But for the most part, everything we knew was self-contained in this particular mass range. And all this information came from the observation of X-ray binaries. So using X-ray telescopes to identify emission from black hole main sequence star binaries. And then, come around September 2015, this sucker shows up in the gravitational waves detected by LIGO and Virgo. This is GW190412. The telephone number just encodes the date it was detected. And what this is showing is the first ever detection of a gravitational wave from two binary black holes merging. And these black holes were already pretty radical compared to anything we'd observed in our own galaxy. The largest black hole mass we'd seen up until then was 15 solar masses, and the claimed black holes masses that were larger than that had some pretty significant error bars around the mass measurements. And all of a sudden, here appears this 30 and 35 solar mass black hole. And in the 5 years since that first detection, 5 years exactly as of a couple of weeks ago, this landscape has already expanded significantly to look something like this. So as of today, we have now entered a regime where the majority of stellar mass black holes have been detected through gravitational waves. And in the last 5 years, our understanding of these systems has radically altered, I would say probably faster than any time since the first black hole detection in 1968. And this is just the beginning of what LIGO and its counterpart gravitational wave observatories can offer us about this new sort of dark side of the universe, right? So we have LIGO and Virgo, which have been under construction since the late 90s, came online for first light, if you call it that, in, I think it was early 2000. At the same time, we have other experiments that are in progress or in planning stages. So the pulsar timing arrays continue to collect timing data, getting better and better constraints on the mergers of supermassive black holes and the stochastic background of supermassive black hole binaries. They just had a very interesting paper come out a couple of weeks ago claiming a tentative low-level signal that might have been attributable to a part of the stochastic background. Circa the 2030s, knock on wood, we're going to see the launch of the Laser Interferometer Space Antenna. It's essentially LIGO in space. The least of people get angry if you say that, but it's true. But by virtue of being in space and having a 6 million kilometer long arm, LISA is going to be sensitive to much lower frequencies than its ground-based counterparts. And will start to give us very detailed looks into the supermassive black holes that merge in the center of galaxies, as well as very early looks at some of the black holes that will merge in LIGO anywhere from hours to decades later. And looking even further into the future, we start to talk about the next generation of ground-based detectors, things with names like Cosmic Explorer or Einstein Telescope, whose initial on-paper detection thresholds suggest that they might potentially detect stellar mass black hole mergers to Z of 10 or beyond. So the things that LIGO is seeing now could potentially be seen in these next generation observatories to massive cosmological distances, potentially before there were even stars that were the progenitors of binary black holes in the first place. And so there's a non-trivial chance that in the next 2 decades, we may be in a position to observe every black hole merger everywhere in the observable universe. Now, as you might have guessed, this statement is something that I put in my talks right around job season time, because it's the kind of thing that looks very flashy on a job season talk. But it's not even filled with that much unnecessary bravado. By the next 2 decades, we might seriously be detecting the majority of black hole mergers that occur within the observable universe. And so what I'm interested in is what can both our local observations and our cosmological observations tell us about the astrophysics that produces these sources, and how can we use this new astrophysical window into the universe to constrain what we think we know about black hole and stellar physics. And so that brings me to the title slide, because I like having a little introduction. The title of this talk was originally The Lives and Deaths of Star Clusters and the Gravitational Waves They Make Along the Way. Because of recent LIGO detections, I'm actually going to switch this up and talk a little bit more about observables from star clusters. But hopefully I'm going to get enough chance to talk about some of the work that me and a few of my collaborators are doing to try and place these results in a broader cosmological and galaxy formation sort of context. So to get a better grip on what I'm talking about, let's start off with a good description of how you actually form a binary black hole in the first place. And roughly speaking, there are 2 sort of domains that people talk about when they want to form binary black holes. The first is that you start off with an isolated stellar binary, give it a couple of O stars, so relatively large masses, and set them with a pretty wide separation, typically speaking a few tens of AU. If you turn the crank on stellar evolution, the primary star will eventually collapse, either as a supernova or as a prompt direct collapse to a black hole. The secondary, as it becomes an evolved star, will expand onto the giant branch, overflow its Roche lobe in what we call a common envelope phase, and then through some process that we still don't have a good physical understanding of, well, we have a good physical understanding of, but there's a lot of uncertainties in some of the details, is what I should say. The presence of this large diffuse hydrogen envelope will cause the primary black hole and the core of the secondary to shrink in their orbit, and at the same time, that injection of energy, are y'all still seeing my slides? It almost looks like the Zoom switched to the other window.
It is working, Carl, no problem.
Okay. Sorry, my computer is just flashing weird things at me. And in the process of losing energy of the orbit into this hydrogen cloud, that injection of energy will in turn liberate the hydrogen envelope from the system. At this point, the core of the secondary collapses into a black hole, and I'm left with a binary black hole that, assuming I've adjusted the knobs on the common envelope just right, will merge within the age of the universe. This is what we typically call isolated evolution, or isolated binary evolution channel. The other way to do this is to dispense with the pre-existing envelope the pre-existing binary entirely, as a way to sort of to sidestep the issues that we have both understanding and modeling the common envelope and dealing with the separation problem, where you have to start these stars off at a wide separation before shrinking them down to a separation where they'll merge within the age of the universe. Now, if I instead start off with a couple of isolated stars, I still turn the crank in the same way, and because they're not a pre-existing binary, I don't have to deal with the common envelope phase at all. But now I have a different problem, which is I have two black holes formed from the collapse of stars, and I need to get these black holes into a binary somehow. Now, normally, if I was to just launch two black holes at one another in empty space, right, positive energy in, positive energy out, there would be no way for me to form a bound system through gravitational dynamics alone. But if instead of just imagining these encounters taking place in the fields of galaxies, what if I instead imagined this encounter was taking place in the core of a dense star cluster, say a globular cluster, a superstar cluster, or a galactic nucleus? In that case, you can imagine that I might have a high enough density of objects that instead of a two-body encounter, this would actually be a three-body encounter. And in that case, if there's a third interloping object nearby, during this encounter, I can actually take some of that excess energy, dump it into the interloping third black hole, or third star, and be left with a bound system. Now, as I said, this needs to be in this core of a dense star cluster, predominantly because that is where we get a number density of black holes high enough for this process to happen with regularity. And at this point, we're pretty sure that the cores of most non-core collapsed star clusters contain anywhere from tens to hundreds of black holes, which enable this sort of dynamical formation channel, which is sort of the second main category of forming binary black hole mergers. Now, I always like to sort of break it down into these two overarching categories, not least of which because, I've done a lot of work on the dynamical formation side, so like placing it in that context, it looks good for me. But in reality, of course, there's a whole host of binary black hole formation scenarios. This is just a limited list of a few of them. And most of these are on pretty good theoretical footings. There's uncertainties in some of them, particularly when you have to deal with either disk hydrodynamics or mixing inside massive stars. But most of these can produce binary black holes that can at a rate that can explain some or even all of the binary black holes observed by LIGO, which is an unfortunate position to be in as a theorist, because we still have this sort of weird theory space oversubscription, where at this point we still have more binary black hole formation theories than we actually do binary black hole observations. I think probably when O3 is done, that won't be the case, but for now it's still true. The question I've spent the last few years trying to understand, though, is instead of just looking at all of these formation channels, is there some way we can tell the difference? Is there some way we can actually model, we can actually look for observables from these different formation scenarios that would allow me to understand better what is, where LIGO and Virgo's binary black holes are coming from? And so to do that, I'm going to just talk briefly about dynamical formation in star clusters. So moving ahead, imagine I have a star cluster formed from a single burst of star formation in a single collapsing giant molecular cloud. The sort of textbook picture of formation for either a superstar cluster or a globular cluster. I was talking to Alex earlier, and we reminisced that this is not actually how we think most globular clusters are born, but for theoretical purposes, it's a useful enough setup. So I have this star cluster where all stars are born approximately 12 to 13 billion years ago. And very rapidly, the most massive stars in this cluster are going to collapse. They're going to form a population of stellar mass black holes, roughly on about a 10 megayear timescale. Now, at this point, I have a sort of classic dynamics problem where I have a series of massive objects, 10, 20, maybe even 40 times the mass of the sun, traveling through a sea of stars. And as we all know, in this particular scenario, the massive object is going to gravitationally pull some of the low mass field stars towards it. And if it's moving with some velocity, as that happens, the massive object is going to build up a wake of stars behind it. This is the process we typically call mass dynamical friction. And as an end result of this, the massive particles are going to segregate into the center of the cluster. Now, the exact timescale for this depends on the masses of on the relaxation time of the cluster, the masses of the black holes and the stars. But for a typical either globular cluster or a superstar cluster of similar mass, this process occurs on roughly 100 megayear timescale. And after that is complete, I essentially have a mass segregated cluster whose core is largely dominated by a dense nucleus of black holes. And so unlike the rest of the star cluster, or the surrounding field of the galaxy, I now have a high enough density of objects where these three-body encounters that I was talking about actually can occur with relative regularity. So once I form a three-body binary, I have essentially a problem that is oddly reminiscent of something in particle physics. So I now have this gravitationally bound binary hanging out in the center of a star cluster. And you can imagine this setup is very similar to a particle scattering experiment. I have some giant target with cross-section roughly proportional to the semi-major axis squared, and I'm literally just going to bombard it with other particles, other black holes and stars that are going to come in and essentially gravitationally perturb the system. Now, if you really want to brag about your theorist bona fides, you can write this down using the language of Feynman diagrams. I, as much as I have pretenses to it, am not actually this much of a theorist, so I like putting this in talks and then never talking about it again. But it's a nice way to sort of classify by energy, sort of the possible encounters that a binary can undergo in the middle of a cluster. However, because unlike Feynman diagrams, where you're just representing actual probabilities, for these three-body encounters, these are actual physical states that occur during an encounter between a binary and a single star. So what I'm going to show now is actually a small in-body scattering between a binary and a single star. And what you see is that the single star comes in, it perturbs the orbit of the binary very slightly, and then it undergoes several intermediate states where the binary and the single object can exchange energy and angular momentum until eventually the interloping star in teal actually ejects one of the pre-existing binary components out into space. And when that happens, you can actually show that on statistical average, as long as the binary is what we call a hard binary, so that's defined as a binary whose either orbital velocity is faster than that of the incoming stars, or more accurately, whose binding energy the magnitude of whose binding energy is larger than the typical kinetic energy of an interloping star. On statistical average, what happens with each one of these encounters is that an object comes in, it liberates some binding energy from the binary. Why is it going backwards? Don't know what that was all about. Shrinking the binary and converting some of that binding energy into the kinetic energy of the binary center of mass. So object comes in, subtracts binding energy from the orbit, giving you a more tightly bound binary, knocking it up into the halo, and then recoil knocks it out into the halo of the star cluster. Now, once it's out there, dynamical friction takes hold again, brings it back into the center, where it's now once again immersed in that giant, essentially gravitational black hole mosh pit in the center of the star cluster. This happens again and again, and at each step, you're essentially setting up a competition between two separate timescales. On the one hand, you have the typical gravitational wave merger timescale between, that is the time it takes gravitational waves to drive this binary to merge. And if that timescale is significantly less than the typical timescale between binary and single encounters, then the binary merges in the cluster. On the other hand, if the gravitational wave merger timescale is much greater than the typical timescale between successive binary single encounters, then what you end up with is essentially a scenario where you've ejected the binary completely out into space. Eventually, one of the recoils is going to have a velocity so large that it's actually greater than the escape speed of the cluster, and it ejects it down out of the cluster, where it may or may not merge many gig years later. Now, the nice thing about this setup, though, is that because this process will essentially continue until one of these two outcomes is realized, the only thing that sets the properties of these binaries is the escape speed of the cluster. Essentially, as long as I have a binary there, it is going to continue hardening without limit until it either merges or is ejected from the cluster. And the nice thing about this is that even though this is formally a chaotic process, right? Like I have a collection of stars that is gravitationally interacting with anywhere from 10 to the 5 to 10 to the 7 particles. It is controlled by the three-body gravitational problem, which is formally chaotic. But despite that, it's actually the bulk properties of the cluster, the escape speed of the cluster, that controls the semi-major axis of ejected binaries. And the in-cluster binary, and a higher escape speed means I have more opportunities for the binary to merge inside the cluster before it's ejected. And so for the ejected binaries, at least, I can write down, even though this is a formally chaotic process, I can actually predict exactly what the semi-major axis and in-spiral times of these binaries is going to look like just based on the number of particles in the simulation, which is itself a proxy for the escape speed. So even though this is a formally chaotic process, the distribution of semi-major axes just looks like a log normal in semi-major axis space, which is pretty cool. Because if you think about it, because this is all well understood Newtonian dynamics, there are no dials or free parameters once I have my initial conditions and my initial star cluster. I just have this big ball of stars, it's interacting gravitationally, and it follows well understood gravitational dynamics. Now, at least a couple of y'all have probably just had the thought, yes, but I'm glossing over the initial conditions, and that is completely true. I would argue that is actually the biggest uncertainty we still have in these simulations, and I'm going to try and address that a little bit at the end. So going back to this initial picture and initial question I posed, which is there some way we can tell the difference between these various formation channels? The original idea we all had, circa maybe 2016, was that maybe there were different intrinsic properties of the merger rate itself that could tell us the difference between these formation scenarios. So perhaps there were differences in the masses or the mass ratios, or maybe even the merger rate that we could use to discriminate these different formation channels. Unfortunately, it turns out if you don't keep a close eye on your theorists, they can go off and essentially mess around with some of the knobs such that most of these theories can explain any of the masses or merger rates observed by light. So that is out. And then what I started doing over the course of my Pappalardo Fellowship was to basically re-ask this question in a slightly different way, which is I changed the question from, can we tell the difference based on just the masses of the merger rate, to, is there something we can use in relativity itself, in our understanding of these systems, to differentiate between different formation channels? And what I'm going to talk about now is some of the intrinsic relativistic properties of these systems, things like the spins or the eccentricities, that might allow us to discriminate these various astrophysical theories. I put masses on here twice because, as I'm going to get to at the end, it turns out that the spins couple to the mass in an interesting way that might help us discriminate these populations. So moving on, and I'm going to start by talking about eccentricity. So if I go back to this picture here, where I said that you basically need a third body in order to dynamically create a binary in a star cluster. Remember, I said that you needed the third body in order to subtract some of the energy and angular momentum from the system. Because if it was just two unbound Newtonian particles interacting, that wouldn't necessarily, you would have no way of going from total positive to total negative energy and creating a bound binary. The thing is, of course, we're not dealing in a Newtonian regime. We're explicitly in a relativistic regime when we're talking about black hole binaries. And so there are other dissipative processes that might allow us to form binaries just from even two-body black hole encounters. And in particular, the most obvious one for this problem are the gravitational waves themselves. And so if you imagine that I allow for the possibility of gravitational wave emission during close encounters between two-body objects, you can imagine a scenario where the two bodies come in, they sort of hyperbolically deflect off one another, and right at pericenter, you actually emit a burst of gravitational waves that is sufficiently energetic, that is, it carries enough energy away from the system that you go from total positive to total negative energy. So to demonstrate what I mean, I'm going to show the exact same simulation that I showed before. So this is the same three-body encounter, has the exact same initial conditions, but this time I have added to the equations of motion the V over c to the fifth power correction coming from post-Newtonian theory. This is also called the 2.5 post-Newtonian correction, and it's the first in the post-Newtonian series where the emission of gravitational waves starts to come out. So this is the same encounter that we showed previously. Already right off the bat, you're going to notice that this is a different encounter. It's already taken a slightly different turn. I've sped it up in the middle here because it's a little too slow otherwise. But eventually, these two particles are going to come back in. They have many opportunities for close paracenter passages, close encounters, until eventually two of the particles get so close together that they emit a prompt burst of gravitational radiation, merge, and actually get a slight recoil kick that ejects one of the particles from the system. Now, if I zoom in on what happened there, right at that point of capture, I'm going to zoom in right where those two orange black holes got close enough to one another. On the top, I'm going to show the actual binary aspect of this. And on the bottom, I'm actually going to show in real time, or real simulation time, forgive me, the gravitational wave, the cross-polarization of the gravitational wave observed from looking face on to this binary black hole. And so what you see is you have this highly elliptical binary, and instead of a normal in-spiral, you actually see individual pulses of gravitational waves right at paracenter. Now, because this is a highly eccentric orbit, the orbit starts to experience significant paracenter precession, which itself encodes into the gravitational wave, and very rapidly you go from binary formation all the way down to prompt merger about 90 days later. Now, this happens on an extremely rapid timescale compared to most gravitational wave-driven in-spirals. Your typical delay between binary black hole formation from, say, isolated binaries to binary black hole merger can be 100 million years. Your typical delay for binaries that are ejected from a star cluster can be giga-years, or even longer than a Hubble time. Here, this prompt merger occurred in 90 days after the first paracenter passage in the middle of this encounter. And so people have been looking at this for many, many decades, going all the way back to the first relativistic in-body simulations in 1993. The first, I think, scatterings that really looked at this in the LIGO context were from Gultigan, Miller, and Hamilton. And the person that really clued us into this, and that really got us sort of interested in this, I put my own humble contributions in the bottom right, was actually Johann Samsing, who wrote a series of papers with Morgan McLeod and Enrico Ramirez Ruiz, really exploring what this would look like for LIGO. And to give a sort of idea of what this would look like, this is from one of my papers from a couple of years ago. What I'm showing right here is the eccentricity of the binary black holes at a gravitational wave frequency of 10 hertz. So binary black hole forms, it goes through the entire process of its in-spiral all the way up to essentially a few seconds to hundreds of milliseconds before merger in LIGO. And right when it first enters the LIGO band at 10 hertz, we can ask the question, what eccentricity will these binaries still have? Now, for isolated binaries, which at least in the cluster context we refer to as primordial binaries, the eccentricity is going to be around 10 to the minus 6. LIGO is never going to be able to detect that kind of eccentricity. But if I instead throw in all the other ways of forming black hole mergers inside a star cluster, the total distribution looks like this. And I can break this down into the contributions from binaries that are ejected from the cluster before they merge, binaries that merge inside the cluster, which have higher eccentricities, and finally, those gravitational wave captures, which merge very promptly after their formation, and still, because they merge so rapidly, have significant eccentricities even into the LIGO band. And the reason this is interesting is because LIGO can ballpark detect eccentricities at 10 hertz of about 0.1 or higher. And what you'll notice is that about 5% of these objects, 5% of all binary black hole mergers from star clusters, will have eccentricities greater than 0.1. The other upshot of this is that roughly half of the binaries, because of this gravitational wave emission, will actually merge inside the star cluster. And that's going to be relevant for the masses point that I'm going to get to in a minute. So eccentricities, as I just shown, can be used to discriminate these two populations. Isolated binaries will never produce a significant eccentricity in LIGO, whereas from star clusters, up to 5% of the binaries will actually be formed with measurable, or will actually merge with measurable eccentricity in the LIGO-Virgo band. So let's ask about one of the other points I've got here. Let's ask about the spins. So black hole spin, of course, is a sort of an intrinsic quality to black holes. And that intrinsic quality actually couples to the gravitational waveform. So what I'm showing here is an image of a spin-aligned binary black hole, where the two spins are aligned with the orbital angular momentum. And as I rotate those two spins into the plane, you're going to notice that the gravitational wave that I've drawn on the right is going to change. So this two spins rotate down, and you're going to actually notice that the gravitational waveform begins to have these sort of amplitude modulations in it. It begins to show this sort of beat pattern. And what's happening there is because the spins are now misaligned with the orbit. Sorry, I thought that was going to be a movie after that. No, I guess I cut that out. And so LIGO, going back to this real quick, can not only measure the magnitude of the spins, but it can measure the orientation as well. If the spins are misaligned with the axis by about 90 degrees, you'll actually start to see differences in the gravitational waveform that LIGO can explicitly measure. Now, how do you get spin-orbit misalignment, though? So if I assume, and this is a pretty big caveat, that my stellar spins are initially aligned with my orbital angular momentum, and that there is essentially minimal tidal realignment, then the spins of my final binary black hole are going to entirely come from the misalignment of the supernova. So the spins start off misaligned, the orbit itself gets whacked around a little bit by the supernova explosion, and the only spin-orbit misalignment I'm going to get is from the slight misalignment of the orbit during those supernova. And you're limited into how large that misalignment can be by the fact that the binary still needs to be bound after the two supernova epochs. So ballpark, although this number is flexible and can get as high as 30 or 40 degrees, for the most part, for most reasonable supernova kicks, the spin-orbit misalignment from isolated binaries is probably going to be around 0 degrees. Contrast that with dynamical formation in a star cluster, where the spin-orbit misalignment is going to be completely isotropic. You expect your spin-orbit misalignment to essentially follow a sine theta distribution, the same way it would for the latitude on a sphere. And so one of the things that we showed, and that a lot of people have talked about, is that LIGO, it turns out, can measure, can get some information on the spin magnitudes, but it can really measure the projection of the spins onto the orbital angular momentum extremely well. And so a lot of us made a point for a while that the projection of those spins onto the orbital angular momentum, this so-called chi effective value, would be a good discriminant between isolated binary formation and formation in dense stellar environments. Because if you expect isotropic distribution on the sphere, half the time you should have a positive value of the spins, half the time you should have a negative value of the spins projected onto the orbital angular momentum. Whereas for isolated binaries, you would expect essentially roughly spin orbit alignment times whatever the magnitude of your spins is. And so this was a great idea we all had, that you might be able to measure a bunch of negative chi-effective sources and be able to say, oh, these clearly came from clusters. And then from the first LIGO observing run, instead, what we found was that the majority of systems were actually consistent with having 0 spin, or 0 chi-effective. Now that could mean that essentially we're sampling the sphere. So most of the time my spins are going to be at 90 degrees, because that's where the majority of my support in sine theta is. Or it could just be that the black holes have low spins. It is entirely possible that perhaps black holes born from stellar collapse simply do not have a good way to transport angular momentum into the final remnant, and instead produce black holes with very little spin. And that question, that possibility, starts to take us from spins back into the argument of masses that I was talking about. So if I go back to this picture here, where I have a binary black hole that merges in the center of a star cluster, when that merger occurs, I'm left with a remnant whose mass is roughly speaking, the sum of the two masses of the components that went into forming this binary, and a spin that is roughly a dimensionless Kerr parameter of 0.7. Now, if both of those component spins were spinning at the maximum allowed limit by general relativity, so they were spinning with a Kerr parameter of 1, it turns out my binary black hole remnant would actually get a pretty significant velocity kick. Because when the spins are with large spins, I no longer have an axisymmetric system when the binary merges, and I actually get an asymmetric emission of gravitational waves. And so in this case, I have these two spins. I'm going to basically have all the gravitational waves come out at 90 degrees to the plane, and I get this huge escape, and I essentially get these huge what are called gravitational wave recoil kicks. They can be as high as 5,000 kilometers a second, marginalized over the sphere. They typically are around 1,000 kilometers a second. And for your typical, say, globular cluster, which is what I've talked about for the most part, the escape speed is anywhere from 10 to 100 kilometers a second from the center. And so in that case, most of these merger products are going to get shot straight out of the cluster. That's way above the escape speed. Black holes will merge in the cluster, and they'll just leave and start roaming the galaxy, as black holes are wont to do. But on the other hand, imagine that what LIGO is telling us is not that the spins are all at 90 degrees to the axis, but instead that the spins are essentially zero. In that case, the gravitational wave emission is roughly axisymmetric. I get no net kick, and in fact, the majority of my binary black hole merger products will be retained in the center of the cluster. Now, once they are there, that dynamical formation process continues. I can find myself another partner and potentially merge again. We typically refer to such a setup as a merger between a first generation black hole, so something born from a collapsing star, and a second generation black hole. This is what we would call a 1G plus 2G merger. I'm actually going to skip ahead a little bit, just because I'm running a little shorter on time than I expected. And if I ask the question, what does my mass distribution my total mass distribution of binary black hole mergers coming from clusters look like as a function of spin, I can actually break this down as a function of binary black hole generation. So what I'm showing now is the total mass of binary black holes from star clusters. And if I break on the right, this is the detected distribution, and I'm showing just the systems that we have observed both in LIGO and Virgo from the O1 and O2 observing runs, as well as several candidate black holes that have been identified from an independent analysis done by the IAS, done by a group at the IAS. And I can break this contribution down into the contribution from 1G plus 1G systems, that is, mergers where both components were born from the collapse of stars, and 1G plus 2G systems, where one of the components, the 2G component, was itself a remnant product of a previous binary black hole merger. I can, of course, take this one step further and ask, how often do I see mergers where both components were formed in a previous merger? And in that case, you can actually see, this is in green here, I get this large population that extends all the way up to a total mass of 160 solar masses in the detected distribution, with a nice peak at about 140, 150 solar masses. If I similarly look at the spin distribution of this, I would expect most of these systems to be centered around 0, just because they're isotropically distributed on the sphere, and that chi-effective parameter is going to mostly be 0. Chi-effective is just essentially the dot product of my spin vector with the orbital angular momentum. So most of the time it's going to be at 90 degrees because there's more support there. And most of the time I'm going to have a chi-effective of 0. And what's wild about this is that in this particular simulation, I started off assuming that every black hole born from a star gets a chi-effective, or excuse me, gets birth spins of 0. So I assume that no black hole coming from a star gets any residual spin. But even in that case, it turns out that dynamical formation, because it is repeatedly merging these objects and converting their orbital angular momentum into spin angular momentum of the remnant, will produce black holes with remnant spin. And you can see on the right that my detected distribution is centered around 0, very similar to what the distribution from LIGO and Virgo looks like, but with a wide tail that is entirely coming from the large spins that are allowed by dynamical formation. And so people have asked the question, is there some way I can use this to sort of constrain the 1G plus 1G versus 2G plus 2G contributions from LIGO? The first paper I know on this came from Davide Gerosa and Emanuele Berti in 2017, followed very quickly by a paper by Maya Fischerbach, Dan Holtz, and Ben Farr. And they were basically able to show that within, roughly speaking, 100 observations, LIGO would be able to constrain the relative populations to extremely good precision. This is from a toy model in the Gerosa and excuse me, Berti papers. I, however, am a little bit impatient, and I didn't really want to wait for 04 when we could get 100 observations. And so the natural question that I've been asking for the past couple of years is there a unique black hole mass that cannot be achieved by single stellar evolution? And of course we know the answer is yes. Above a roughly speaking 50 solar masses, it turns out that massive stars undergo what's called a pulsational pair instability supernova. Essentially, once you get above about a stellar product of about 50 solar masses, it turns out that your massive star essentially completely explodes in a massive burst of pair annihilation, leaving behind no remnant. And so this is from a population synthesis study done by Chris Belchinski, where he added in a prescription for pulsational pair instability, and essentially beyond above about a total mass of 80 solar masses. So that's 240 plus, that's a 40 plus a 40 solar mass black hole. You essentially do not get binary black holes from the isolated channel. Compare that to this dynamical model, where we suddenly see a huge number of objects inside the pulsational pair instability gap. And so I've been giving this talk for about a year and a half now. This is based on a 2019 PRD, and which itself was following on a 2018 PRL. And the basic claim was that if we use these collisional models of star clusters and we make assumptions for the initial black hole spins, we can identify, if LIGO were to detect something in the pulsational pair instability gap, that would be strong evidence of dynamical formation. And of course, and I'm sure most of you all have heard of that, that leads to this, the recently announced GW190521, a binary black hole detection from the LIGO-Virgo collaboration. This black hole has the binary, has a total mass of about 150 solar masses, and their parameter estimation suggests that the primary black hole mass was about 85 solar masses and lies within the pulsational pair instability supernova gap with a probability of less than approximately 99.7%. So this is our first evidence of a system that can only be formed through some dynamical process. And in a lot of ways, it's kind of a perfect poster child for what you would expect for dynamical formation. So the mass posteriors, like I said, this is showing the posterior probability distributions from LIGO. And the point basically says that if I plop on top of the primary mass, the pulsational pair instability gap, this object almost certainly falls within that 55 to 120 solar mass gap, where you cannot form a black hole from a single star alone. At the same time, we had all focused on the masses, but the spins of this object also show a significant magnitude and a significant spin orbit misalignment. And so remember how I said that even from dynamics, because a lot of the time your black holes are going to be lying in the plane, So most of the time, you're going to see a net zero chi effective. In this case, the posterior probability distributions from LIGO suggest the spins are actually near maximal, or more likely around 0.7, so exactly what you would expect for a merger product, and lying about 90 degrees of the plane. So the way to read this plot on the right is that they are essentially spin tilt plots. Higher color means higher magnitude, and it basically is showing the theta angle that is the angle between the orbital angular momentum and the spin angular momentum of each black hole. And so both the primary and the secondary, assuming they have large spins, appear to be at about 90 degrees to the orbital angular momentum. So that is a strong indicator of dynamical formation. And it just keeps getting better and better. These two plots were taken directly from the LIGO paper, from one of the LIGO papers, which I embarrassingly have to apologize. I left off the citation on these slides. But there were a couple of papers that came out after this, which even found that there was evidence of eccentricity in the signal itself. So this is from a paper by Romero-Shaw. And what she was able to show was that using eccentric gravitational wave templates from LIGO, there was actually strong support for a large eccentricity at 10 hertz, in this case an eccentricity of about 0.13. Such an eccentricity is virtually impossible to produce from an isolated binary evolution channel. You're absolutely not going to get this from a massive stellar binary. But contrast that to our initial predictions from 2018, and it turns out that an eccentricity that high is fully consistent with a gravitational wave capture inside of a dense star cluster. So this is really the first event, I would claim, where we have strong evidence of dynamical formation. And it's very, very vindicating to see that a lot of the work that myself and plenty of other people have been doing seems to match up well with these predictions. Now, I want to stress that even though I am now strongly convinced that this event was formed in some sort of dense stellar environment, that doesn't mean that all of them were. And we still have a lot of work to do, both theoretical and observational, in order to constrain which events are coming from where. I think of this as more the first, I think of this in a little bit parallel with the history of GRBs, where for the longest time there was tons of theory work done on GRBs and different formation channels, and there was a huge oversubscription of theory space in terms of what could explain what, until eventually we got a single GRB that was observed in an identified counterpart. And that started to really constrain some of the available theory space. So I've got about 10 minutes left. I want to talk about what I actually put on the abstract, which was formation of star clusters and how that relates to LIGO events. But this is a good time to stop and ask if anybody has any questions.
Are we raising hands on the chat or?
Whatever works.
I have a question. Thanks, Carl. I'm wondering, so this is a really cool, like, sort of smoking gun evidence of dynamical formation. How easy is it to sort of go from this back into the total population? Like, what fraction of all of the mergers are coming from dynamics? Or is it not?
So that's a pretty easy statistical calculation to do. I haven't done it yet for two reasons. One, LIGO has not released their full O3 catalog. And what they've released instead is a couple of exceptional events. And they're still preparing the full O3 catalog. And it would be statistically, statistically crappy of me to basically take the 10 events we have so far, plus LIGO's 3 exceptional events, which were essentially just hit with a statistical estimator of things that would get published in PRL, and then try to do a population-based analysis on that. So if all of the, and the other problem is, of course, I've been a little agnostic as to which dynamical formation channel this came from. I personally think it is pretty strong evidence for formation in either a globular cluster, superstar cluster, or a galactic nucleus. But there's a lot of wiggle room within those 3 different populations. The galactic nucleus one in particular, there have been some arguments that it could have been formed inside the disk of an AGN. I think there's a lot of theory work to be done there before we can say that in particular. And so unfortunately, backing this out into theory space would be a little bit difficult. But from star clusters like globulars, to give you an example, if this roughly, roughly 3% of all mergers from globular clusters are 2G plus 2G mergers, and the fraction that are this large inside the mass gap is roughly, 3% of all detections from a population of globular clusters would be 2G plus 2G mergers. And about half, I think a third of those would have, I'd have to check those numbers, would have masses inside the pulsational parent stability gap. But again, I would want to do a better statistical analysis with LIGO's full third observing run before saying for sure.
Awesome, thank you.
Sure. Okay, I'm gonna take the last like 6 or so minutes and just rapidly go through this argument right here. So one of the things I've been working on recently was to sort of remember I said that it's optimistic but entirely reasonable that we might, within a couple of decades, be sensitive to every black hole merger everywhere in the universe. And I also claimed that our dynamical formation scenario essentially has no dials or free parameters, and it's all just well understood gravitational dynamics. Now, the second part of that statement is true. Once we have our initial star cluster configuration and our initial collection of in-particles, it's just a question of turning the crank and seeing what comes out. There is, however, a big asterisk here, which is that the initial conditions themselves need to be taken into account very carefully and have a strong influence on what sort of population you actually get out of this. So one of the things that I've been doing lately is trying to better understand how our initial conditions affect these estimates, and then to try and place what we model for these globular clusters in a better cosmological context. So my first stab at this took place a couple of years ago when I was still a postdoc. In a paper with Avi Loeb, we basically took a cosmological model from Kareem El-Badri, who's a grad student at Berkeley, who created a very compelling semi-analytic model of globular cluster formation using essentially halo merger trees from cosmological simulations. So we basically took this, combined it with some of our Monte Carlo models of star clusters, and we're able to produce cosmologically motivated estimates for what the black hole merger rate as a function of redshift would be from globular clusters across cosmic space and time. And we were also able to compare this to other formation channels. So in this particular paper, we took isolated binary estimates from Chris Belchinski, combined that with our cosmological model for star cluster binary black holes, and even combined this with an estimate for the merger rate caused by black hole triples, taken from some work that I'd done with Fabio Antonini and some work that I'd done with a student at MIT. And using self-consistent stellar physics, we were able to show how all of these different rates combine with the cosmological history of star formation and the history of sort of globular clusters and superstar clusters in their galaxy. So this was our initial stab at this. But what I've been doing more recently with some collaborators in the FIRE collaboration is to try and self-consistently do this within a galaxy simulation. So this is the latte simulation from Andrew Wetzel from a few years ago. And essentially what we've been doing is trying to combine, I realize I did not put my Carnegie Mellon logo in these slides, whoops, is essentially trying to combine a model for a formation of a Milky Way-like galaxy with detailed simulations of cloud collapse and fragmentation and star cluster formation from collapsing GMCs, and combine this with our Monte Carlo models of star clusters, our in-body models of star clusters. And by doing all this, we're trying to get out a fully self-consistent population of dense star clusters that experience all the relevant physics for star cluster formation and evolution within an assembling Milky Way-like galaxy. So in doing so, we basically start off with some GMC, using a lot of the work from Mike's PhD and now postdoc research. we essentially have a way of transforming from a GMC that is a series of particles that appear to be collapsing inwards, and extracting from that a catalog of masses, radii, and metallicities. We can then track the orbit of this galaxy within the fire simulation and extract relevant environmental details like the strength of the tidal force, the velocity as it's traveling through the galaxy, even the dynamical friction timescale for the star cluster to spiral into the center of its galaxy. And so one of the things we're trying to do, hoping this will come out in a few months, though I really cannot believe how much people were lowballing how much teaching consumes of your time. So it's probably going to be when I get a break. Is that we basically took this population of initial clusters, extracted from one of these galaxy simulations, and evolved them forward using a fully collisional in-body code. We ended up with a population of final clusters that had been significantly reduced, particularly at low masses, and then creating a larger cut to those that survived dynamical friction all the way to z equals 0. We ended up with a population that looks like this. For comparison, the Milky Way globular cluster population looks something like this. And I would argue that we're actually getting the majority of the globular cluster population right from about 2 times 10 to the 5 solar masses up to 10 to the 6. We're missing a little bit in the a few times 10 to the 5 range, but overall the shape, at least the high mass end, is correct. What we're missing at the low mass end, I suspect, is actually something called tidal shocking, which is well known to contribute to the disruption of low mass clusters and puffy clusters as they pass either GMCs or other gravitational shocks in the galactic potential. But ignoring that real quick, what we found that was interesting was that the majority of our clusters actually formed in the local universe at essentially z of 0.8 to z of 1. And now this is interesting because most of these clusters actually tended to have high metallicities and be forming typically after what we would expect for Milky Way-like globular clusters. And as we were looking through this result, LIGO announced one of their earlier binary black hole candidates from this year, GW190412, which is an observation of a binary black hole with a 30 solar mass black hole merging with an 8 solar mass black hole. And now the reason this is interesting is because, one, it has a much lower mass ratio than on most of the objects that LIGO has seen so far. Most of the objects LIGO has seen have been consistent with having mass ratios near unity. And the second is that the 30 solar mass object appears to have a spin of roughly 0.43. And so we wanted to ask the question, can you produce objects that look like this from our population of star clusters from this galaxy simulation? So we looked at a particular one of the massive star clusters, something I nicknamed Behemoth. And we extracted from it the various properties that sort of controlled its evolution in the galaxy. And then just follow this forward in time. I'm gonna go ahead and try and finish up here real quick because I'm now over 3. And what we found was that there was a population of things that looked like this particular unique black hole event coming from this massive superstar cluster that were actually 1G plus 3G binary black hole mergers. So in this case, most of the stellar mass black holes in this superstar cluster were born with masses around 8 to 10 solar masses, but because the escape speed of this cluster was so freakishly large, it started off at nearly 300 kilometers a second to escape from the center, and even by the time it spiraled into its galactic center, it still had an escape speed of 100 150 solar masses. I'm so used to talking about that. 100 to 150 kilometers a second, that you're actually able to retain even some fraction of 1G plus 2G mergers. And in doing so, we were actually able to show that repeated mergers inside these massive star clusters can produce things that look like this particular gravitational wave signal, and that uniquely populate both the mass and spin parameter space where objects like these are created. And so that takes me to the end of my talk. I want to thank you all for staying a couple minutes afterwards, and I'd love to answer any questions people have. And if not, thank you very much.
Thanks a lot, Carl. And so if you have any questions, maybe we can take a few brief questions here. So you can raise your hand in the hand raising part. Okay, and I can maybe start. So I was wondering, Carl, how long time does it take before the binary black holes merge inside of the cluster? Would there still be gas around that would maybe create an electromagnetic event from this?
In the superstar clusters in most of the globulars and superstar clusters, we assume that the gas has been expelled by the collapse of the O and B stars. And in particular, when you have your supernova that produce low mass black holes and neutron stars, we assume that that's enough to expel the gas. So you wouldn't really expect an electromagnetic counterpart from a binary black hole merger like this. I know there was a claimed electromagnetic counterpart with GW190521, which has led some people to speculate that it was actually formed in an AGN disk. I can't comment really on the AGN formation channel overall, but I will point out that I'm a little skeptical of the EM counterpart claim for that signal, not least of which because the transient came approximately 35 days after the gravitational wave detection and was at about 100,000 Eddington luminosity for a black hole of that mass. So it's certainly possible, but I think it's not exactly the smoking gun I would personally like in order to claim that this came from the AGN channel.
Okay, thanks. Tony has a question.
Yeah, thank you for the nice talk, Carl. I was just curious about extending, you focused on black holes, but there's also neutron stars, and neutron stars will be somewhat segregated in these environments, maybe not as much. Have you explored or thought about whether you'd have maybe G2 sort of, types of objects from maybe neutron stars that merged previously and are now merging again and so forth?
So we've looked into neutron star mergers in at least classical globular clusters. So this is work led by Claire Yee, who's a grad student at Northwestern. Unfortunately, what we've discovered is that so there's two problems with this. The first is that the mass segregation, as long as there are black holes left in the cluster, is so complete that you actually don't end up with the neutron stars in the center where it can undergo these three-body encounters. The second problem is that it turns out that there's a symbiotic relationship between the black hole dynamics in the cluster and the overall evolution of the cluster itself. So typically speaking, when a cluster is born, it starts to undergo core collapse. There's a natural gravitothermal tendency for the inner parts of the cluster to shrink as the outer parts of the halo expand. This is related to sort of heat flow, if you want to think about it thermodynamically, of the stars in the center sort of towards the outer part of the halo. And the way this is arrested is that eventually the inner parts of the cluster will continue to shrink without limit until a binary is formed. And once you have that binary, that single black hole binary becomes the power source for the rest of the cluster. A typical hard binary in a globular cluster has the same binding energy, roughly speaking, as the entire star cluster itself. And so that one binary black hole becomes enough to essentially hold up the cluster against continued collapse. Because as I throw other objects at it, they each get recoil kicks from their binary single interactions, which in turn gets deposited as energy into the star cluster. It's essentially the same kind of self-regulation that you see in stars themselves, in that the nuclear reaction rates, adjust themselves in order to be in hydrostatic equilibrium with the star. Or excuse me, the reaction rates don't, that was a misstep, but the actual amount of energy extracted is adjusted in order to maintain hydrostatic equilibrium with the star. The problem with neutron stars is that they are sufficiently low mass that you can't really dynamically separate them from the rest of the cluster enough to extract energy from them in the same ways. In order for this to work, you have to have a system that is close to what's called the Spitzer instability. And for neutron stars, just based on their mass, you would have to have roughly 10% of the cluster be comprised entirely of neutron stars in order for the cluster to extract energy from neutron star burning the same way you do black hole burning.
Great, thank you, Carl.
Do we have other questions? I have more questions if no one. Okay, I can ask my question. So, Carl, you mentioned that the merger product of the binary black holes in the clusters, they reach a really high speed once they have merged, several thousand kilometers per second. And I could be mistaken, but isn't this enough to even escape the galaxies that they are born in?
Oh yeah.
Wouldn't that mean that you are creating lots of massive black holes in the intergalactic medium? Does this have an impact in some way?
Huh. I mean, you would certainly be ejecting these out of their galaxies into the IGM. I have no idea if that would be. I have no idea if that would be observable or would have some sort of impact. I'd never thought about that.
Okay, it would be cool.
Yeah.
It would maybe be nice to calculate the density. I don't know if that's going to be seen.
Yeah, I mean, the density will be pretty low just because, well, the short answer is no, I haven't thought of it, but that's pretty cool. I guess it would be interesting to see how, I mean, this only works though if you have large spins for the black holes to begin with. And this was people's claims for originally why you wouldn't be able to retain the merger products of supermassive black holes in the center of galaxies, right? If you have two supermassive black holes merge, I mean, 5,000 kilometers a second is enough to eject you from even the nuclear star cluster, at least in a relatively wimpy galaxy. But yeah, I have no idea what the implications of just a bunch of free roaming heavy black holes or supermassive black holes in the IGM would be.
Cool. Okay, so we have taken a little bit long time, so I think we're going to wrap up here. And please sign up to talk to Carl. I sent around the schedule. And thank you so much, Carl, for a very nice presentation and coming to visit us, although it's virtual.
No, thank you very much. It was great to get to talk to everybody.
Thank you.